All right, building models, machine learning models using sklearn. So sklearn, as you guys have probably figured out by now, is an open source library that we can use that has already a lot of pre-built functions for data mining and machine learning. And it's built on top of a lot of other existing packages, such as NumPy and SciPy and Matplotlib. So as we learn about these algorithms, we're going to learn the formulas for them. We're going to learn the cost functions, how they're optimized, the way that they are scored. So if we think about linear regression, which we just learned about last time, we learned the formula for that the output is a combination of weights times these feature inputs plus some bias term. And we maybe don't want to code that ourselves. Maybe we don't want to write a function that says, give me all of your x variables, and I'm going to multiply them and add this bias term by these weights. And then I have to write a function that finds the weights, that minimizes those weights to reach my highest performing outcome. And then also I have to check and validate all the input to make sure it's things I can multiply by, and you're not just passing in like a string, for example, that's going to throw an error into my program. And so sklearn has handled all of that for us. So when it comes to building these machine learning models, it's actually a pretty lightweight and pretty powerful tool for us to just pick up and apply, because they've already implemented all of these algorithms in code. And they have a large range of algorithms. That's one of the best things about sklearn is they have linear regression, decision trees, support vector machines. They're constantly coming out with more. And when they do release one, it leverages all of the same structure and framework that the other ones have leveraged as well. So you don't have to constantly be learning a new way to apply this or a new way to apply that. So it's got a lot of pre-processing tools, which we'll touch on a little later in the course, which are very, very powerful. There are some ways in which you can build model pipelines that are really robust for model methodology and have solved a lot of pain points and hurts with deploying models to production. And it has a lot of all your model evaluation metrics that you might need, which we'll talk about more in the next, not the next immediate class, but the following machine learning module. And cross-validation, which we'll talk about more later. Anyways, there's a lot of useful stuff. So today we're going to start playing with this. When you do machine learning, there's sort of a process called machine learning methodology, which is a series of steps that we take when we build machine learning models in order to build models that perform well, that generalize to unseen data. And if you violate some of these steps, you are at risk of producing a model that doesn't generalize well to unseen data. We're going to build on this methodology. And today we're going to start with these 5 steps. This is not exhaustive by any means, and there's a lot more we need to put into this, but instead of throwing the whole gambit of you guys all at once, we're going to build on that throughout this course so you can get really familiar with the core pieces and then understand how it might change in different situations and why it's important. So of course you need to import your libraries. What you'll find is that everything we work with in Python and we work with in sklearn are already pre-built libraries, which is great for us because the less stuff we code by hand, the less likely really it is that something will go wrong. Then we need to go get our data. In this class, we will primarily be reading from CSV files or using already pre-baked packages in sklearn because we don't have a substantial amount of time to learn how to connect to a database and how to get that data. But when you build models in real production environments in the real world, you're going to have to probably load data not from a CSV on your computer. So you're going to have to connect to data sources and read those into Python. There can be really almost infinite number of different ways in which you can do that. I'm happy to chat more about that in office hours if you guys have questions for how to actually read in data at your own workplaces. But this is for our uses, we will most likely just be working with CSV files or something to that effect. Then in machine learning, you're going to want to split your data into a training set and a test set. So if we have a data set that we give to our model, and we give it every single data point we have, because the more data you give a model, the better it is, right? The better it performs. More data, more performance. Well, if you give it every single data point, how would you evaluate how well the model is doing? How do you know how it might perform on something called unseen data it's never seen before? So if you give it all of the data and you give it 100% of your data, we're training on houses. We give our model every house we've ever seen for the past 10 years. And then we put it into production, which means a new house comes on the market and we don't know how much it's going to sell for. We give that model that house and then we wait a couple months and then eventually it sells along with some others. And what we'll probably see something is a difference in our performance metric. We'll see what we thought our model would perform at. Maybe when we trained our model, we said, hey, it had a 95% accuracy. It did really well. But when we implemented that model in production, it looks like it's only performing at 80% accuracy. And that's because when we asked the model how well it was doing, we gave it data that it already seen before. We gave it our training data to evaluate its performance. We gave it the same data that it had trained on, and in effect, our model cheated because it said, hey, I've seen something kind of similar to this before. In fact, I've seen this exact same thing. And this is how it performed at that point in time. And so we don't want to do that. We're in machine learning, we're sort of experimentalists. We employ the scientific method. So we very scientifically and very methodically create test sets that represent unseen data. Now in this class, we're just probably going to do train test split, and it's going to be really fairly straightforward. We're just going to split the data set. We may do some shuffling or something to that effect to make it a little bit of a better split. But when you're building these in the real world, you're going to really want to spend a lot of time thinking about how you create that test set, because that is going to be your only measurement of how well your model's going to do. And you want that to be as close to the real world as possible, as close as it will be to putting it into production as possible. So we'll talk more about that as we go. This is all we're going to say on it today. 5 bonus points on your assignment if you do that in there, but we're not going to talk any more about that until probably next week. So train model is the part of the process in machine learning where we actually instantiate a new model. And when we say instantiate, that means it chooses random values for the weights. So when we have our linear regression, it might choose 5 for M or beta sub naught, and it might choose 10 for beta sub 1. Just a random values chosen for our weights. It hasn't learned anything about what the optimal weights are yet. Then we hand it our data. It employs its optimization algorithm, and then it learns the best weight. So training your model is the part where it learns, and then evaluating the model is taking that already statically trained model. It's not changing the weights anymore. The weights are what they are. It's learned the best thing, and now you're giving it 2 things. You're giving it the true answers, what were in your test set, the ground truth, reality, and you're also giving it what it predicted. You're asking it to make a prediction, and you're comparing what did the model predict versus what is the ground truth reality in my test set. We're going to go through those steps in code, I think about 3 times today. Here's the first time. Okay, so we are going to look at a housing data set. Don't get too excited. It's not the same as the one on your assignment. So some work to do, but you can definitely use this as a template, as an example, how to answer those questions. So the first thing that we are going to do is we're going to import some various libraries. With NumPy, you do not have to do as NP. Technically, I could import NumPy as anything. I could say import NumPy as this is a really cool name, and that would work. And now every time I said this is a really cool name, it's actually calling NumPy. So you can, it's called aliasing. We can alias NumPy however we would like. I will tell you standard just convention and things that you'll see on the internet is to call it NP. So if you want to make your code just a little more readable by other data scientists that are also going to be seeing your code, be nice to them, call it NP, call pandas PD. Again, you can call it whatever you want. So anytime you see as, this is just somebody shortening the name of a package. Okay, so we have pandas, we have NumPy. Now we're also going to import a data set that exists within sklearn called the California Housing Data Set. And so sklearn has data sets that actually exist within the package. You don't have to import a CSV. You don't have to read the data from anywhere. And they're really great because you could just get working with building a model and learning sklearn without doing anything else and not having to worry about how do I read in data. So that's what we're going to do today. So this should run on your computer without you downloading any CSVs or moving anything. This used to be something called the Boston Housing Dataset, and the California Housing Dataset is different. So this is not the same as the one that you have in your assignment. If you look at this dataset on sklearn, you will find that it's actually an aggregate. Oh, look, it even gives me some nice information if I hover over it. So you'll find that it's actually an aggregate of houses in an area. So there was some bias problems with the Boston Housing data set. There was some representation issues. It wasn't ethical. And so they removed it and they replaced it with this data set, which has been screened and is a better representation. And so this is an aggregate data set. So you're going to predict the price for a house based on like the average price of a house within a region. So it's blocks. They grouped houses into blocks. So they're not individualized houses. So we're going to import train test split. sklearn has a bunch of different folders, basically, that have functions inside of them. So in the model selection, you'll see a lot of different functions. One of these functions we're going to import is train test split. In the sklearn linear model, we're going to import linear regression. In sklearn.metrics, we're going to import mean squared error and R2 score, R squared. Okay, so these are some import statements. You guys may find as you run your code, you'll have to import other things. In Python, it is the convention to put all of your import statements at the top. I'm not going to dock you any points if you don't do that, but that is convention, standard convention, if you want to make your code more readable for your friends. So step 2, we're going to load the data set. This one's pretty easy, so let me import my functions first. This one's pretty easy. We're going to fetch California Housing, which is a function we imported from sklearn. We're going to call that function. Anytime you see a variable followed by 2 curly braces, that means we're calling a function. And so now we have this thing called housing. Let's just look at what that is. So we have this thing called housing, and oh, that's interesting. It looks like it's a dictionary. So we have a key of data, and then it's followed by a value of an array that has a whole bunch of data that doesn't look super readable to the human eye. We have a key called target. Oh, look, this must be the list of our target values we're trying to predict. We have a key called feature names, and it's only got one in there, and it's called, feature names. We've got a key called feature names, and we've got a list here. So we've got, I don't know, several feature names here. So what I did here is I took our housing in dictionaries. You can call the dictionary, and then when you hit dot, you can call a key. So we can call housing.data, and that will actually give us that array. So we called data, which was this key, and it gave us the value of that array. We can call housing.featurenames. So we can call the key feature names. See, the key here is feature names, and it gave us its value. The value it contained is this array. We know that's the value because it's on the right side of this colon. Okay, that's how dictionaries work. And so what we're going to do is we're going to pass those into a pandas data frame. So we're going to pass housing data and feature names into a pandas data frame. And I should even make this more explicit by putting the word data here. There we are. So pandas data frame, let's look at that. Okay. Here is our pandas data frame, pd.dataframe, and this can take in a lot of, a couple different variables. So you can pass it data, you can pass it index, you can pass it columns, you can pass it none. You'll notice sometimes that when you're working in code, people will do things like I had in here just a moment ago, where they won't pass the keyword of the variable that they're trying to define. So for example, what if I just did this and I didn't say I wanted to assign it to data. I just said housing.data. Python is intelligent enough to infer that you are passing one thing, so that must be assigned to the first parameter. If you pass two things, it's probably the first thing is the first parameter, the second thing is the second parameter. If you pass three, it assumes first parameter, second parameter, third parameter. The reason I had to add the columns equal is because notice I passed the data, and then I skipped index, and then I passed columns. So the column names that I was trying to pass would have been part of the index one. So anyways, if you just want to make it easier on yourself, just explicitly call what you are trying to pass it to. So in this case, I just said I'm trying to pass housing.data to data, and I'm trying to pass the housing.feature name to the column so that my columns have feature names. Okay, so let's look at what that looks like first before I even add this other column here. And let's look at what it would have looked like if, so pandas data frames, by the way, if I just run it like this and I don't assign it to anything, it will print it out, but it won't store it anywhere. So you have to assign it to a value. You have to give it something to be called. In this case, we're calling it df. That's kind of convention. All right, so here is what this data frame looks like. You can see that we have all of our feature names and all of our features. Now, what would have happened if I hadn't passed those feature names? Data. Oh, look, we have a bunch of data, but we have no column names. It just says 0, 1, 2, 3, 4, 5, 6, 7. So that is why we had to take those feature names, because this array has there's no headers in there to name our data. Okay, so we notice that we have all of our data here, but we don't have our target variable. We just have income, age, average room, so latitude, longitude, population. So we have to add that. And in Python, the way that you add a new column is you do df, and then you index into the column of your data frame. So fun fact, if you just wanted to look at median income, we could do df at this, and it would give us that column, right? The way that you make a new column is you take that exact same syntax, select a new column, but if there's nothing with that name, it will create a new one, and then you assign it some values. So df at price, housing.target. Now if we look at df, this is our df, and it has a column price. So this line here, we're saying df at price equals housing.target. We're grabbing from that housing, remember housing was our dictionary here. We're grabbing target, and remember it's returning this array. When we say housing.target, remember it returns the value for that key. So it's a list of numbers, and now this is our entire data set. So here's our data set. X features across the top until that you get to this last column. This is our Y target. All right, we are going to train, test, split your data. Here's your bonus points for your assignment. We are going to create a split into a training set that is 80% training, 20% test. That's all we're going to do for this class. We'll talk more about that in the next block of machine learning about train, test, split when we talk about cross-validation. So X is all of our X features. So we're going, typically, you'll have a data set like this where everything is just in one sheet. That's why I combined them all so you can see what that looks like. And you will have to split 4 machine learning models into your X features and your Y features. It's a little weird because I just added them together and we're going to split them. So in that case, we're going to do df.drop. We're going to tell it to drop the column price. You have to say axis equals 1 to tell it that it's looking for a column and not a row. If axis equals 0, it's looking to drop a row. If axis equals 1, it's looking to drop a column. And then we're going to set our Y variable to data frame at price. So let's just look at those real quick. Let me run this, and then let's look at X. So X is now this. See, we just dropped our target variable. And Y is now this. Here we are. This is price. So Y is just a list of prices. That's all it is. And we're going to call this function from sklearn, which we imported above. That's where this function comes from. And we're going to pass it 2 things in the beginning. We're going to pass X, and we're going to pass Y. We're also going to tell it that the test size is 20%. It infers that since we're saying the test size is 20%, that the training size is, of course, 80%. And then we're going to pass something called a random state, which is a random seed. That means that if you run this code on your computer, you get the exact same individuals, the exact same houses in your test set as I get on my computer. So if you take the random seed out, every time I run this, it shuffles it slightly differently, and there will be slightly different people or slightly different houses in your test set, just by the random nature of programming. And so this makes your code reproducible, something called reproducible for other programmers. So if you put a random state or a random seed in, it means it makes the exact same random decisions every single time.
Hey, Emily?
Yeah.
I think I missed, why is it random state equals 42?
Oh, that's such a great question. I love that you asked that. All right, this will be fun. Let's see. Let's go, I don't want to click on Reddit. I don't know what's going to pop up there. Medium seems safe. All right. Shout out if you guys know, by the way. It is because of the book, The Hitchhiker's Guide to the Galaxy, where the answer to life is 42. So basically, programmers think they're funny, and it's sort of like a popular meme thing. And now it is just truly common practice in programming, which I think is hilarious. So Hitchhiker's Guide to the Galaxy, it's because the meaning of life is equal to 42. But really, in reality, you can set this to whatever you want. So truly, you can make this 1, 2, 3. It's whatever your random seed, whatever you want it to be. You can make it 0. The number that you put in here is how it determines that random seed. So if I make my random state 0, you make yours 0, they're going to be the same. but you'll see 42 a lot on the internet as you're looking through examples. Okay, that's a great question. Next, we are going to, so we've got our data, we've got our X, and we've got our Y, and we set a random seed, and we've got our test size. Cool. Let's train a model. So we learned all this stuff about linear regression, and maybe it's a little disappointing that at the end of the day, it's just 2 lines of code. So we're going to import our model from sklearn, which is called linear regression. We're not going to pass any parameters. We're just going to do a base model. Now, there are fancier things that you can do. So let's look at the linear regression package here. So this is linear regression in sklearn. And you can see that it has several parameters that it can take in that you can change here in linear regression. So getting familiar with how to read sklearn documentation is going to get you guys a very, very long way in machine learning because you can see how many different linear models there are. Here we are. Here's all your linear model packages in sklearn. So there's quite a few. So understanding how to actually use them and apply them can be very useful. Sometimes there's very complex topics that you may not need to worry about until later, like njobs allows you to do some like parallelization. So you can run multiple computations at the same time. So you don't necessarily need all of these, but they're helpful to learn. So just start looking at the documentation, start becoming familiar with it. If you scroll to the very bottom, almost always there's example code in how to do this. So you can just go click on the package, look it up on sklearn. It'll tell you what you need to import, and then it'll give you an example. And this will get you a long ways too, reading through this and trying to understand, okay, reg.score, this is how you pass X, Y, this is how you get the coefficients, this is how you get the intercept, and this is how you make predictions. It's really quite well done documentation.
Dumb question.
Yeah.
At the top, what is in the arguments that you pass? What is the star, like the barrier you talk? The first thing is the asterisk.
This here,
Yes.
let me look at one thing real quick. And
It's not a so, sorry,
no, let me get back to you on that. I have some guesses and some assumptions. I'm not sure if I want to make those guesses or assumptions right now. It could be one of two things, maybe some inheritance going on, or it could just be arg parser, or not arg parser, but args taking all other arguments in. It's a good question. I wonder if it's just inheriting from linear model and then it's taking any additional args from that, but let me check it out.
Okay.
It's a good question. Okay. So that is our linear regression that we imported at the top that we're going to call right here. And we're going to assign that to a model. If we just call it, we don't store it anywhere, it goes away. So we have to store it into a model. And then once that model is, this is called instantiation. We have instantiated that model. Now it exists and it has like some random weights assigned to it. We're ready to fit it. So this is our training. sklearn has two main functions that you will see in every single model, most models, for the ones that we're going to talk about: fit and predict. And sometimes you will see them separate, and sometimes you'll see a function called fit predict. But this is a very a very, very common structure, and it even extends to, a form of this even extends to their processing and their pipelining that we're going to talk about later. So they have these sort of structures that they built that it's the same process every time you build a model. Fit takes in two things. It takes in the X variables, and then it takes in your Y variables. So give me some features and then tell me what you're trying to predict and tell me what those true values are. You notice that in sklearn, or the convention is to do X_train and Y_train. And again, X will be, convention is to make, you don't have to do this by any means, but convention is to make X capitalized because we are working with a matrix. Remember, we said little x is one instance, big X is an entire matrix. So big X represents this entire data set. Y is little because it is one dimension, because it is just one list, right? So Y is a little y. So that is convention, big X, little y, when your Y is one dimension. And when what's returned from train test split is a tuple of four different variables. So X train, X test, Y train, Y test, it does have to be in this order. Order matters here. Technically, you can call these whatever you want. I can call this A, I can call this B, I can call this C, CD, and I call this E. It doesn't change what train test split returns. Train test split doesn't care what you call your data. So make it easier on yourself and just use easy to understand words for your training and test set. What it does return is the 20% Y will be in this last position, and the 20% X will be in this position, the second position, or the first position if you're doing Python indexes. So when you say test size equals 20%, the 20% for the X will be here, the 20% for the Y will be here. So order matters. So just call them X_train, X test, Y train, Y test. So now you have two data sets, two data sets, training and testing, and each data set has two variables, a training set and a test set. So did I say that right? No, I didn't. An X data set and a Y data set. So you have two data sets, a training data set and a test data set. Each data set has two attributes to it, two variables, a X dimension and a Y dimension. There we are. Okay. So we have to our model, it's looking for our training. So don't put your test in here. That would be bad. Put your training in here. Now, when we go to make our predictions, this is when you give it our test set. Notice the difference between fit and predict. In fit, you have to give it a Y. In predict, you do not, because there is no Y. Because this function, model.predict, this is what it will call in production as well. This is what it will call in the real world. So now we've trained our model, and we want to see how well it does on unseen data. So you call model.predict, and you give it your test data, your X data, and you ask it to make predictions. So what this looks like, I don't think I ran this one yet, is here we are. It's an array of predictions, just like our ground truth data set is. And since we set that Y test aside and we never used it at all for anything, it wasn't used at all in the training here. See, we used the Y train and the X train. In here, we can now pass in our Y test and our Y pred to our scoring metrics. You'll notice what's really great about sklearn is no matter what scoring metric you use, they have the same structure and the same way that you pass in this information. So it's Y test, Y pred, Y test, Y pred. So Y test is our ground truth. This is our lock and key data set. This is our test set, our real house prices that we set aside. Let's look what that looks like. Oh, look, you can already see some, oh, sorry. There we go. Oh, look, you can already see some differences. Oh, look, this one was 0.719. This one was 0.470. That's not very close. This one doesn't look very close either. Okay, so let's see what it says in terms of performance. Ooh, that's not so great. 0.55 in terms of mean squared error, 0.7 for our R squared. So not very good. So there's probably some things we could do to improve this model on a range of 0 to 1. That's almost getting close to random, to just a coin toss, which means you have a pretty terrible model. So no good, no good. And we can see that these numbers kind of, at least the first three here, kind of reflect that. Okay, keeping with time, I'm going to keep moving. So that's an example. I'm trying to decide if I should, if there's time, we'll come back and we'll do this breakout. And I have the same structure. I'm asking you to load the data set, and then you guys are going to apply this on your own. You're going to train the model, make predictions, evaluate the model. So use that same structure that I gave here and much of the same code. I just didn't put it in there for you, but for a different data set. So this is the diabetes data set. And in this case, you're trying to predict the progression of the disease. So you can see that, again, it is a scalar value. It's not a categorical value. So this is not a classification problem. This is a regression problem. So we're trying to predict a number, 1.41, 1.42, 2.7, etc. Okay, we will come back to that if we have time here. For now, we're going to keep moving, and then we'll take a break after probability, which this is a very short section here. So let's jump into probability. Okay, so probability, just to preface here, is a topic that we're not going to be able to spend enough time on. It is extremely important to machine learning. It is the fundamentals and the underpinnings for everything these models do, but we do not have the time to give it the attention it really deserves. I'm going to do a 5-second overview of this, but it really warrants more attention. I can't emphasize that hard enough. If you guys have any time on your own, exploring more about probability will pay a lot of dividends for you. I would strongly encourage it. And I'm happy to point you to resources, or if you have questions, what should I learn more about? I'm very happy to guide you through that and to give you some more self-learning and self-driven resources. We just don't have time to emphasize as much on it because we're going to focus on the machine learning algorithms. But at a very, very high level, machine learning in the context of statistics and machine learning, probability represents the likelihood of an event occurring. So when we say the probability, we're really measuring, quantifying how likely, what's the likelihood that this will occur. And probability ranges, and one of the most important things for you to know is that probability ranges between 0 and 1. You cannot have a probability of -2, and you cannot have a probability of 1.5. It is bounded between 0 and 1. 0 indicates that the event will never occur, and 1 indicates that it will occur with certainty. So when we are predicting something in a probabilistic model, you don't have to ask someone what 0 represents or what 1 represents when you're saying, predict, is this a banana or not? We always just assume that 1 is, yep, certainty of the event, certain that it is a banana, and 0 is impossible. It's impossible that that is a banana. Typically, it falls somewhere along the range. So we're looking 0.2, 0.3, 0.7, 0.8. And the probability of A, probability of the event, is the number of favorable outcomes over the total number of outcomes. There's different types of probability, and this is probably a gross oversimplification. So people from probabilistic theory will be upset by this, but there is maybe a theoretical probability. That is, what is the probability of flipping heads on a fair coin? Well, we can use some reasoning and some assumptions about that, and we can say that it's 0.5. Everybody, kind of generally talks about flipping a coin as a probability of 0.5. There's also experimental probability. So if we actually ran an experiment, we had an actual coin and we flipped it 45 times or flipped it 100 times and it came up heads 45 of those times. Well, that probability is 0.45. It's 45 out of 100. This may be clicking with you guys as some of your probability things come back. A lot of the stuff that we build in machine learning is technically conditional probabilities. It means we're asking, what is the probability of A, given all this information about an individual or about an instance or about the world. So given B, what is the probability, what is this a probability that this is a banana, given I tell you the color of it, given that I tell you the size of it, given that I tell you the shape of it, given all this information, given our X variables, what is the probability of A? So that's the only thing I'll say about conditional probability. So in terms of likelihood, here's a visual representation that might be helpful in understanding our models. And remember, this gets back to some models are useful, but all models are wrong. All models are wrong, but some are useful. So when we think about probability of 0, that's the impossible section here. So none of that is filled up. As we increase our probability, the event is more likely to occur. So in this instance, that little dial, this red spinner, is more likely to land on those blue segments as more of the segments are blue. There's a higher likelihood that when you spin this dial, if it spins evenly and it's well tuned, it's going to land on these blue dials. And we can think about machine learning models like this. When it outputs a probability, it's saying, hey, it's very likely that this event will occur, but what it is not saying is that this event will for sure occur. I know with 100% certainty, I can see into the future, and this is magic. It is all statistics under the hood, and it's really all probability based. I think it's just very important to ground in that reality and not make undue assumptions of grandeur of some of these models. So the definition of probability is it quantifies some uncertainty that the event will occur. So this example is just to take you back to maybe you had a probability class that talked about dice, and you've got a 6-sided die. And on one side, it's 1 dot, and on another side, it's 2 dots, on another side, it's 3 dots. So what is the probability that you will roll a 4? It is 1 out of 6 because there is one event that is a 4 out of all of the events that exist that could possibly occur. And in that situation, there are 6 events. So this is important as we think about classification and how many potential classes we could classify something into, how many potential events. So there are a lot of machine learning algorithms that use probability, one of which is logistic regression, which we will talk about today. Okay, one more thing to say on probabilities, and that is probability distributions, because I do think this terminology is used. You do not have to know any of these formulas. We're not going to go through these formulas, but I want to explain, I want to build some conceptual understanding for a uniform distribution, example of an exponential distribution, a normal distribution, and a Bernoulli distribution, just because I do think it, and I want you guys to understand the difference between predicting something that is continuous and predicting something that is discrete. So let's do that. So if we are, I'm going to flip around this computer, and we're going to move over to the whiteboard. So forgive me here. Oh, that is, it should stop sharing. Yeah, that's good. Okay. All right, here is what we're going to do. All right. When our models make predictions, we're going to start with the uniform distribution. So there is, when you're trying to think where to start. Okay, let me start here. When our models make a prediction, they're not just necessarily making one prediction. They're making a set of predictions. So if we are predicting, I'm trying to think of it. Let's say we're predicting salary. $1, $70, $100, $50, whatever. So we're making a whole set of predictions. And if we take all of these numbers and we plot them onto, and we plot them onto a graph where we say our predictions are this x-axis here, and the values are this y-axis here. For something like salary, you'll be able to see what is the shape of that. For example, salary will look like this. It will, there will be a lot of people with a really low salary. And as you get towards the end, there's going to be like a few Jeff Bezos out there, right? So it's going to get really, really small. Just a couple Elon Musks. And so not a lot of people make this much money. But then there's going to be quite a few people in the middle, and then there's going to be a lot of people who don't make a lot of money. So that is a specific type of distribution. So in our distribution list, which I realize you guys can't see because I'm not sharing, but that's our exponential distribution. So salary is an example of an exponential distribution. Okay. This is all I want to get across to you guys. And the other one I want you to know, just so that if we talk about it, hey, this is a uniform distribution. A uniform distribution is something like that dice, where we had 6 different outcomes, and the probability of each outcome was exactly the same. So we had the 6-sided dice. The probability of rolling 1 is exactly 1/6. The probability of rolling 2 is exactly 1/6. The probability of rolling 3 is 1/6. 4, 1/6. 5, 1/6. Okay, so that's a probability, uniform probability distribution. The other type of distribution that I want you guys to know is a normal distribution. And a normal distribution, some people call it a bell curve distribution. There's a lot of natural representations for this in the world. So you can think about height like this could be one. This is where there's not a ton of short people. There's some short people, like myself. There's not a ton of tall people. There's some tall people. But most people are average height. So you get to the middle and there's an average height here. Grades are often normal bell curve distributions. So a couple people fail the class. People do fail classes. People do get 100% in the class. But for the most part, there's like a bell curve representation for what people might get. So that is grades. There is one more I want you guys to know called a Bernoulli distribution, and that is when we have 2 outcomes. So this is when and I have a better picture of this on there, but maybe we're doing heads and tails. Maybe we're doing heads and tails, but it's an unfair coin. There we are. So the probability of heads is actually, let's say, the probability of heads is 0.75 or 0.3. The probability of heads is 0.3, and it's a gambling guy, and they're rigging us. So the probability of tails is then p minus 1. So it's p minus 1. If our probability of heads is 0.3, probability of tails is p minus 1, so that it has to be, or 1 minus p, sorry, 1 minus p, so that it has to be 0.7. So this is our probability of heads, and this is our probability of tails. Otherwise, maybe this is 1 and 0. So this is a Bernoulli distribution. These are the 4 ones that are fairly relevant for anything that we'll talk about in this class. I want to note one more thing, and that's continuous and discrete. So when we look at salary, in this case, the instance I described is a continuous instant. And that means that this point and this point and everything in between these 2 points is valid. That means, let's say, that means $100 is valid, 100.1 is valid, 100.11111 is valid. That is what a continuous distribution is. The values and everything in between those values are valid potential outcomes. So this is salary is a continuous variable. When we do regression, it is on continuous variables. Height is also a continuous variable. So you can have, and grades, if we're measuring it in a numeric scale, meaning 98.7, 98.8, 98.9 is also continuous. If we measure grades with A, B, C, D, their letters, that means it is not continuous. So that would be the discrete. So dice, these outcomes for dice, these are discrete outcomes. That means you can be 1, or you can get a 2, or you can get a 3, but you can't get a 1.5. There's no 1.5, it's not an option on the dice. There are discrete outcomes, and you can't have an outcome in between. You can't have 1.17. You can't have 3.27. It doesn't make sense. That is discrete. This is also discrete. Bernoulli distribution is also discrete. We are predicting that it's heads or tails. It cannot be half heads and tails. Unfortunately, in this diagram, it cannot be lands on the side of the coin and spins. It's either heads or it's tails. There's no in between. So that is discrete. So those are the 2 things. You can either be continuous distribution, or it can be a discrete distribution. It just depends on what we're trying to predict. Okay, I'll take a picture of that and send that to the people online. We are going to jump back into the slides. Now I have one picture for a Bernoulli distribution, and then we're going to take a break. Give me a moment while I get everything hooked up, because I unplugged my computer, so it'll just take a second. There we are. That came up nice and fast. Okay, let's share this screen so you guys can see the last slide, and then we will take a break.
Bernoulli always 2. You can't do 1 2.
Bernoulli is always 2, but it is a very particular instance of a type of distribution that can have more than 2. It's, yes, Bernoulli is always 2. I can send more on that one. Okay. Sure. Okay. Good deal. Okay, Bernoulli distribution. Here is a much better graph than the one that I drew. I was trying to mimic that so you would have a representation of this to map that to. So this is a Bernoulli distribution. And remember, if P, whatever your value for P is, your other one has to be 1 minus P. Because in probability, everything has to sum to 1. All the potential, if you take all the potential outcomes, it has to sum to 1. So fun fact, when you look at large language models that are popular in the world today, some of the calculations that they run under the hood to determine and predict what is the next word, they're producing a probability for that. And that probability for that word is compared against all other potential words that could possibly exist. So the number of potential outcomes is usually thousands. You might say, hey, there's more than 1,000 words in the English language. How is that possible that it's only thousands? Well, basically they break words down into smaller chunks so that the amount of potential outcomes is actually smaller. So if we think about the word baseball, for example, it's not its own word. Maybe one of the words in our corpus is base and ball, so baseball would actually be 2 tokens combined together. That was just a fun extra piece of knowledge. You don't need to do anything with that, but it is just to say that even in large language models and some of these very sophisticated machines, our probabilities will all sum to 1, even if you have 1,000 different potential outcomes. You take the sum, some of those will be infinitely small, infinitely tiny, such that they do not matter. However, everything does sum to 1. That's all you need to know about probability for this course. And we're going to take a break here, come back in 10 minutes at 7:45, and we will talk about logistic regression. I will mute and go off camera, but I'll be here. Okay. Let's jump into what you guys are here for. Logistic regression. All right. Logistic regression is another machine learning algorithm, a machine learning formula that we can apply to classification problems. So you guys remember in the first session, I said there's different types of machine learning problems. There are supervised learning problems and there are unsupervised learning problems. And under the supervised learning problems domain, there are classification problems and there are regression problems. The regression problems, we talked about those. Those are continuous output variables that you're trying to predict, continuous target variables. So house prices, you're trying to predict someone's salary based on some information you know about them. Logistic regression is for classification problems. This is where we're going to use that Bernoulli distribution. We're going to do a two-category distribution. So maybe I should have started with this. This describes a situation in which we might use it. You're a healthcare provider and you want to predict whether a patient is at risk for developing diabetes. And you don't know whether they will develop diabetes or not because they haven't developed it yet, but you want to understand if they're at risk for it, if they might develop diabetes in the future. And what you know about them is some medical information. Maybe you know their age, maybe you know their BMI, their blood pressure, you even measured their glucose levels. Maybe you have a lot more data about them because you are a doctor. And you want a model, you want to use a machine to help you understand what is their level of risk. What is the probability that they are at risk for diabetes, where being at risk for diabetes is a 1 with 100% certainty and not at risk is a 0. So this is the problem. What we're going to apply, sorry, I was trying to decide what order to talk about these in. What we're going to apply to that is logistic regression, which is a statistical model for binary classification. We're predicting the probability of an outcome and the probability that it belongs to one of two categories. Either it's an apple or it's not an apple. Either it's a banana or it's not a banana. Either it's spam or not. Either that individual responded to a mailing campaign or they did not. Unlike linear regression, which predicts a scalar outcome value. So why not linear regression? I think this is a very reasonable question to ask because linear regression predicts numbers. Why couldn't we just ask linear regression to predict this outcome, give it a bunch of examples of 0 or 1, and ask it to make a prediction? Well, linear regression predicts continuous values that range from negative infinity to positive infinity by default of this algorithm and default of the formula. It is not bounded, it is not constrained, it's not restricted to only give you a range of 0 to 1. So what that means is you could technically, within the realm of this formula, get back, you could ask it, hey, what is the probability of this person being at risk for this patient being at risk for this outcome? Is it 0 or 1? And it could tell you 7. And you wouldn't really know what to do with that answer. So it's not suitable for this classification problem because the algorithm does not bound it to 0 and 1. And because it does not bound it between 0 and 1, there's no way to really interpret that. The advantage of logistic regression is we get a probability, 0.7, which is very interpretable to us. It's very familiar to us in what we see in the world today, and we can really understand that that's a pretty high likelihood, and that has some serious outcomes with it, and that's fairly close to 1. Linear regression does not have that same probabilistic interpretation. It's not bounded between 0 and 1, so it doesn't represent probabilities. Furthermore, the logistic regression gives us a tool called a decision boundary, which we will talk about more, so I won't talk about it too much here, but it's a tool we can use to basically say, well, saying everything that's greater than 0.1 is 0.5 is a yes, and everything that's greater than 0.5 is a no is not useful for me. I only want you to say yes if it's greater than 0.7 and no if it's greater than 0.7. So basically, a decision boundary means we can slide this and we can adjust the way our model makes decisions based on probability outcomes. I'll talk about that more. But first, let's talk about logistic regression. So we understand why we want to use it and why it's important for this problem. So here is the function. A logistic regression equation is the probability that y equals 1 given x, given all of our feature variables x, and it is equal to 1 over 1 plus e. This is a mathematical number, by the way. This is not a variable. This is a mathematical constant. You can look up what is the value of e, and it's sort of like pi. You know, it represents, it has a numerical representation in math, so it's an actual value. So e to the power of negative, and oh my gosh, what do we have here? We have beta sub naught plus beta sub 1 plus and times x. Doesn't this look super, super familiar? Who can tell me what this is?
Y equals mx plus b.
Woo! This is y equals mx plus b. Yes, this is linear regression. So something that is probably not emphasized enough. And remember, I told you there was a reason we learned linear regression. It's so that we can understand this formula, because imagine coming in and looking at this formula without knowing linear regression, without knowing that this was the formula representing that. It might look overwhelming, but it's not overwhelming to you because you understand linear regression, you understand that formula, and now you understand that this is just a transformation on linear regression. That is all this is. By the way, this is something called a sigmoid function, and this is crucial to neural networks. I promised you that we would build towards neural networks, and this is the piece right here. So I promise this is very, very important to understand. I told you I'd only give you useful stuff by the end of this course that would build towards large language models and neural networks. And in neural networks, a sigmoid function is one of the activation functions. So this is important. So this is our linear regression formula. And in this instance, they only have, they got the y equals mx plus b for simplicity here. But we know that you can add many features here. So we know that this could really be, the way this should really be written, and I don't want to go to the work of moving my computer and going over to the whiteboard again, but if I had a whiteboard, what I would actually, I'd scratch out this beta sub naught plus beta sub 1. I write beta sub naught plus beta sub 1 times x sub 1 plus beta sub 2 times x sub 2 ... beta sub n times x sub n. So this assumes one feature. This is your logistic regression function if you only have one feature. You're trying to predict diabetes, but you only have age. Now, if we wanted to add more features, extend that parentheses out and add more betas with their own weight, beta sub 2 times x sub 2, and add that on as well. And continue to do that for each feature in your data set. So every feature has its own beta, has its own weight. It's also called a coefficient, has its own coefficient. In neural networks, we call that the betas here weights, except for beta sub naught is something called the bias. So when we say weights and biases, weights are beta sub 1, beta sub 2, all the way up to beta sub n, and your bias is your beta sub naught. So that is the logistic function. Let's talk a little bit about, I want to make sure I captured everything here. Good. I think the most important thing to take away from this slide is the relationship that this has to linear regression, and the fact that all we're doing by adding this 1 over 1 plus e to the negative, notice we're not adding any other information to the problem. We're just transforming this number. And what are we doing to transform it? We're forcing it to be between 0 and 1. That is all this does. When we have the sigmoid function, which takes in a value of z, here's the generalized form of the sigmoid function, which, by the way, in our logistic regression equation, remember the z is our linear regression. Z equals your linear regression formula. It is a function that maps any real valued number to a value between 0 and 1. So what that means is, see this S curve, it's sometimes called an S curve or an S shape, ranges here, and you can see that these values, these input values, these X values, quite literally go to infinity. So you can have all the way out here maybe negative 7,053, and when you put that in, you might get a probability of 0.0000000001, right? It never quite goes to 0, but it gets as close to 0 as possible. On the other side here, you can go to positive infinity, and when we put in 7 million, it is 0.99999. It goes all the way up to 1, right? And if we just round up, then that will become 1. So if we put in 2, somebody tell me what the probability of this sigmoid on this sigmoid curve is if we put in 2. Estimate, just guess based on the picture.
9.
Yeah, that's right. So 8, 9, somewhere in there, right? We can't tell because there's not a number line here, but that's how you can tell. You follow this X value, we input 2, follow this up to where it meets the blue line, and we see on our y-axis here that ranges from 0 to 1, that's probably about 0.8, 0.9, somewhere in there. So that is how you guys read a sigmoid curve. Let me see if there is anything else. The times in which this is relevant to use, let me see what my next slide is. Maybe the next slide's a better example of this. Here's what I want to say. The reason this is powerful, what do I mean when I say it maps numbers, real value numbers, to a probability? Well, there is some probability of you passing an exam versus number of hours studying. So maybe you're in chemistry and you have to study a ton. And there are some students that spend a lot of hours studying, like 5 hours studying for their exam. And those students that spend 5 hours, they all pass their exam. So here on the x-axis is how many hours they spent studying. And these dots say whether they passed or not. So this is a discrete outcome because they either didn't pass the exam or they did pass the exam. There are no numbers in between. They can't halfway pass the exam. But you can see that there is some ambiguity here, right? So if we look at somebody who spent 3 hours studying, there is one individual who did not pass the exam, but there's equally another individual who did pass the exam that spent just over 3 hours. And there are several people who passed the exam and didn't spend quite as much time studying. But generally, there is a trend that we can say the less time you spent studying, you're more likely to fall in this population of people who didn't pass the exam. And the more time you spend studying, you're more likely to fall in this population of people who did pass the exam. So again, this just helps us understand that models are wrong, but some are useful. We don't have a clear decision boundary, but we can use something called a sigmoid function to help us quantify that. So we can say, hey, I spent 2 hours studying. What is my probability of passing the exam? And we can say that, well, you have a 25% probability of passing the exam. I spent 3 hours studying. Now you have a, 65, somewhere in there, % probability of passing the exam. And as you get up here, you spend 4, it gets really, really high, and anything beyond 5 becomes almost certain. So this is how a sigmoid curve works. Given one dimension, such as hours studying, we plug that into our formula, and it outputs a probability between 0 and 1. You can, of course, extend this to multiple features and multiple dimensions. It's just easy to start by looking at one feature in one dimension. But of course, in our examples, when we try to predict disease, we'll be using lots of information about an individual. Any questions on sigmoid curve? It's pretty foundational to data science. All right. Let's talk about the decision boundary. I said we would come back to this. So naturally, I'm going to pop back over to this one just 1 second since we're already familiar with it. Naturally, I can tell you what your probability is of passing an exam or not. And when you ask your sklearn models, there is a function that will tell you, here's the probability associated with that outcome. But oftentimes you don't want a probability, you just want the model to tell you yes or no. So you're not always looking for what is my probability, am I going to pass the exam? Just give me a yes or no answer. Just tell me what it is at the end of the day. Is it spam or is it not spam? Don't tell me the probability. Is this individual going to have the disease or not have the disease? Don't tell me. So what is the answer, quote unquote answer, recommendation from the model at the end of the day? And that is determined by something called the decision boundary or a threshold, a probability threshold. And by default in sklearn and many other packages, if you do not set one, it's 0.5 because that feels natural, right? So if your probability, in this case, 0.5 is right here on our graph. So we're just going to follow that over to here. And that means that any individuals above this line, we would say that they passed the exam. Our model would predict that they would pass the exam. Sorry, not above the line, above this probability threshold, above 0.5. So any of the values that map to above this line. So basically anybody that spent like more than 3 hours studying is more than like, what is that? Like 2 3/4 hours studying, our model would say that they would pass the exam. We can, of course, see there are situations where that is correct. Many of these individuals did, but we can also see there's 2 situations where that's incorrect. Anything on the that is less than 0.5 from a probability, if the model says 0.45, 0.3, 0.2, it would say it would predict that those individuals would not pass the exam. So that is a probability threshold. When logistic regression predicts its output by default of the formula itself is a probability. The way we interpret that formula or the way we interpret that output is with a decision boundary that we can set manually. We can choose this. We can make it 0.9 if we want. And typically by default, if it's greater than or equal to 0.5, then it's predicted as a true outcome. And if it's less than or equal to 0.5, it's predicted as a false outcome. I don't like this picture because it doesn't have any overlapping instances and nothing's perfectly separated like this in the real world. So that's why I liked the passing the exam one better. But this shows that threshold value. Here's a better visual representation of like this. So here's our sigmoid curve here in the middle. Remember that's gray. And in this case, we set our probability threshold to 0.9 instead of 0.5. So here's what that looks like visually. And I don't know what this is on the X and Y axis. I just thought it was a good picture. So in this case, this is where we're trying to predict class X. And this is where we're trying to predict class checkmark. And you can see that in this right panel here, that's shaded in blue, this is everything that the model said was of the positive class. So the model said everything in this blue area was a check mark, where in fact, one of the things in that blue area was not a check mark. That was an X, and this would be a situation in which the model was incorrect. So this is something called a false positive, where you say, yep, this person is going to pass the class, and they did not. Everything on this side of the line, remember we said 0.9, so to find that, you find 0.9 on this y-axis, and then you find where that curve meets the x-axis. So everybody less than our feature variable, input variable, that scales from -1 to 1, which I don't know what this is, but everything less than that, we're saying those people won't pass the class. People who have a -1 attendance or whatever, they won't pass the class. And you can see there are 4 situations in which we got that incorrect. So these are called false negatives. We falsely predicted that these individuals would not pass when in fact they did. So you can see how as you slide, you can imagine in your head, you start sliding this decision boundary down and this window pane starts sliding over. So we'll talk about decision boundaries more in the metrics class and when you might want to use them and how you can use them to manipulate your outcomes to be more representative of what you're looking for, what your stakeholders want. But for now, I just want you to know that that does exist. By default 0.5, you can change it. This is one more thing that I will just tell you what the formula is now. We're going to totally skip it though, because we go over this very in depth in the metrics section. So the next 4 weeks after this 4-week section. And this is like probably our main formula we go over. So I don't want to waste our time on it because we'll just talk about it more later. But this is a very, very, very important formula for neural networks. So we're building to that. And it's in sklearn. In logistic regression, we've talked a lot about decision boundaries. We've talked a lot about this is how the model outputs a probability. But what we haven't yet talked about is, well, how do we determine what those weights are? How do we choose what beta sub naught and beta sub 1 are? How do we determine that should be 1 and not 2, and 2 and not 3? So I told you how the model outputs probabilities. We haven't yet talked about how it optimizes those, how it finds those actual weights, and that is something called a cost function. So we want to penalize our model when it's incorrect, and we want to give it rewards when it's correct. And the way that logistic regression does that is something called the log loss function, which essentially looks at your probability, your predicted probability, which remember we said y hat is your predicted output. It takes the log of your predicted output, it multiplies it by the true output, which if you think about it, it's 0 or 1. So in the case where this is 0, this entire thing goes away. And then we take 1 plus 1 minus the true value, which again is 1 or 0. And if you think about this, when it's 0 or when it's 1, this entire thing goes away. So in reality, again, we'll talk about this, you're either looking at the left side of the equation or the right side of the equation, depending on whether the ground truth is 1 or 0. In the other situations, the other goes away because you're multiplying by a 0. But then in this case, you take the log of 1 minus y hat. So you either take the log of y if your ground truth is 1, or you take the log of 1 minus y if your ground truth is 0. So it looks like a complicated formula. It's really not. It's just very cleverly written. It's a very beautiful formula. And then we do that for every instance. All this is saying is 1 over n. So do that for everybody, add them up together and tell me the average. So it's really not a complicated formula, but it is very, very, very important. And it is used in large language models and outputs from large language models. So when you look at large language models, remember I said that they output probabilities for words and it's over this whole corpus. In reality, what they're outputting is log probability, log probs. If you go do some research on that, you'll find that that's actually a transformation on this log loss formula. So this does not go away at all in your data science career, and it actually gets even more important. But we'll talk about it later. You don't need to know this for the exam or any homework that you do, because I will test you on this next course. Okay, so, but I wanted you to know that there is a way to optimize those weights, and that's what it is. Okay, if you're still kind of confused, like what's the difference? Linear regression, logistic regression. I should have put a different picture here, I'm realizing, sorry. I should have put one that had continuous values so you could see that, but this is a problem, the problem we've been talking about, where we said, hey, I have discrete values, they're of category A or they're of category B, and they cannot be anything else except a banana or not a banana. And this is why linear regression wouldn't be appropriate for that. It would fit a linear line to that, and any values in between here, including beyond 1 and beyond 0, would be valid values for output. And that's really not what we're trying to model. What we're trying to model in this case with a logistic regression is we're trying to output the probabilities associated as an outcome with that X feature. So as you put in X, how do the probabilities change? Ranged from 0 to 1. So really, really key high-level outputs. I'm sure you know this by now, but that is linear regression outputs continuous values. We're predicting house prices. We're predicting salary. So that is a regression problem. So you should all get that correct on your test. And logistic regression is a classification problem. So it outputs probabilities between the range of 0 and 1. The outputs are very different for these two models. So regression task classification. Okay, covered that. And we have 45 minutes left and plenty of time for breakouts. Okay, so we have a breakout, and then we'll pop back into the slides. We'll talk about evaluation metrics on one slide, and then we'll continue. So let's do, I'm on the wrong screen. Let's do our logistic regression breakout, finish the slides, and then if there's time, we'll pop back to the diabetes one, and you guys can do that yourselves in groups or individually. Okay, so remember we went through this sklearn example, and we did this housing where we imported, we looked at this data set, and we split the data, and we made predictions, and we evaluated. So remember all of that code and that structure. How great is sklearn that we're going to use the exact same structure for our breast cancer one, and guess how many lines of code I'm going to change? Okay, I did change the evaluation metric, but assuming it was like a similar problem domain, which it's not, we'll include it. Okay, so let's see, we changed one thing. We changed our evaluation metric. This is the same. This is the same. We had to change this from linear to logistics, so that's different. So that's the second thing we've changed. This is the same, and then we had to change our data. So we changed 3 things, and it's like substantially the same code. Pretty cool. It's pretty cool. Okay, so let's walk through this. Let's import our libraries. We are going to import from sklearn our train test split, our model. Remember, we don't want to go build 1 over 1 plus e to the negative beta sub naught plus beta sub 1 times x. Like, we don't want to build that ourselves. That sounds like a lot of work. So we can actually just use this logistic regression from sklearn. And you know what? Let's go look at that. Here we are. It is a linear model because it's a linear transformation, but you guys know that now. Because we're transforming linear regression. So in this one, there are other things, other penalties you can use. So if I wanted to do a different type of penalty, if I wanted to optimize the model's training in a slightly different way. I wanted to use a different algorithm, a different approach for doing that. Here are the options that I have to me. So I can either do no penalty, and you can see the default is L1. So that's what the default is. But let's say I wanted to do a L2. No, default's L2. Sorry, I say I wanted to do L1. I just want to show you guys what it looks like to change the parameter within an sklearn model. And then I promise we'll go back to the top of this. And we'll walk through it very slowly. So I think it was called penalty, right?
Yeah.
Penalty, and there we are. Oh no, it has to be a string, sorry. There we are. And let's just make sure that runs. Oh, I'd have to change the solver too. Okay, but this is how you would theoretically do it. I have to change a few other things, and I don't want to get too into the weeds when it's not super necessary just yet. So this is the logistic regression, and like all the other ones, there's some other values you can change in here. Might encourage that you guys just explore that. You can read some great Stack Overflow things on it. If you keep going down to the bottom, oh, got to go quite a while. There we are. Here's an example of how you would use it. And CLF, by the way, is used a lot. That's just like classification function. It's just kind of like one of the nomenclatures that they use, or one of the standards they use. You can name this whatever you want, but you of course load in you create your logistic regression, and in this case they're fitting it on the same line. Python is so cool. You can do that. And then they're predicting, and they're predicting PROBA as well. So in logistic regression, remember I said you can just predict, and by default, the predict gives you give me the answer at the end of the day. I don't want the probability, just tell me yes or no. But you can also get the probabilities. So you can do clf.predictProba. This is a different function. So if I ask you to tell me the probabilities, you need to do predict_proba. If I ask you to tell me the actual predictions, you need to do predict. They're different. They're two different things. You can, of course, figure out the predictions from predict_proba. You just take predict_proba and you say, if it's greater than 0.5, then it's 1. And if it's less than 0.5, then it's 0. And that's how you get the output for predict. That's what they do in their code. But they provided it, it's easier for you to just call predict and predict_proba. So this is important because there are some accuracy metrics. I hate using the word accuracy, sorry. There are some performance metrics. There are some performance metrics that ask for the probabilities, and there are some performance metrics that ask for the prediction. For example, what we just learned about the cost function, log loss needs probabilities. Log loss needs probabilities in order to determine the outcome. You cannot just pass it zeros and ones. It will not work effectively. I'm trying to think of what that would do. It would do something really strange. So it needs probabilities in order to determine that. And so you have to pay attention to what your scoring function is looking for. Okay, so let's go back to, all right, so I think we talked about that enough. Where are we at here? We imported our data. In this case, we're gonna load another sklearn data set because I'm being lazy. So we're going to load the breast cancer data set, which is another very well-known, very renowned starter data science data set. And what it has here, let's just go look at more interpretable data here. Oh, I skipped that nice step where we turned it into a pandas data frame and looked at it, right? Because we didn't technically need to do that. Oh, here, I think when we do train test split, it turns it into a pandas data frame by default. No, it doesn't. Okay. Well, let's look at, I think it's called data.features. let's just look at it manually. Data dot target name, target. It's a description, feature names. Here we are. I was close. There we are. Here are the features that we are trying to predict. And let me get our target so you can see that as well. It's good to understand our data. All right, so we are predicting 0 or 1. That's our ground truth set. It's 0 or 1. It is very rare, by the way, that in your ground truth set, you're actually going to have probabilities. Most of the time, people say you either had cancer or not. They would say you had an 80% chance of having cancer. We don't know what that is. We are modeling that with machine learning models to try to understand our world. But in reality, our ground truth set, it's either 0 or 1. So that's why we're trying to predict either 0 or 1. The probabilities just help us understand how we got there. So here are our features. We have like mean radius, mean texture, mean perimeter, mean area. So we took some measurements. So we have some medical measurements about this individual and about their potential breast cancer. And so we took all these data points, and you can read more about what all those are. And that is our X. That's our data.data. All the data that represents that. So we split into X-train, X-test. And I'm going to continue here. And now instead of model equals linear regression, we said model equals logistic regression. And we are going to fit. We're going to pass. Remember, we're passing our training data set here, not our test set. We're going to pass X-train. We're going to pass Y-train. Order matters here. Don't pass Y and then X. Your fit function is expecting the X data set and then the Y data set. So we're going to call model.fit. And model.fit, this is our actual model training process. This is how our model is learning the weights for that function. Remember that logistic function, the beta sub naught plus beta sub 1, it's learning the weights and biases in that sigmoid function. All right, now we're going to make a prediction. So here we're going to pass it test now. We already trained it on the training set. It's already seen that data. It's spoiled data. It's bad data. So now we need some data it's never seen before. That's our X test data. And here we run X test. And we collect the predictions into this variable here. And now we want to know how accurate this model is. And oh, wow, looks like we are doing pretty well. We have an accuracy of 0.95, which rounds to 96% is our accuracy, which sounds pretty great. I don't actually know if that's great because accuracy really doesn't mean anything at all. And we'll talk about why that is the case in the metrics section. So you guys don't really need to worry about metrics and like what's the right metric to use and why accuracy might not make sense here. We'll talk about that next time. I want you to focus on this process here. How do I get the data? How do I get that in? How do I split for bonus points? And how do I train the model? What am I passing to model.fit? What am I passing to model.predict? And then how do I pass something to a scoring function? So I just want you guys to get familiar with kind of the flow there. Any questions on logistic regression? Here, let's look at the, let's look at the model outputs from what I had said. So model is our object, by the way. That's our logistic regression trained object. And so let's look at model dot predict. I just want to see what X test. So remember I said we can put out zeros or ones, or we can put out probabilities. We can also do model.predict predict proba. And that puts out our actual probabilities. Now, when you look at these, you might say, well, that doesn't make sense. You told me probabilities had to be between 0 and 1, and I see 9.9. How can that possibly be a probability? Anytime you see this e to the negative, this means that it is scientific notation. So if I take you way back to your days in chemistry and your science classes, if it's e to the e negative 01, you have to move the decimal over a spot. So this is actually 0.99. And this one, you would have to move the decimal over 3 spots. So this would actually 1, 2, 3. So this would actually be 0.002. So very tiny, tiny probability. So I promise you these two numbers do sum to 1. You just have to look at the scientific notation, or you can just you can round those two if you want to look at them differently. But just so you know, when you see that, these two numbers, by the way, are when you do predict proba. These two numbers are, one is the prediction of the 1 class and the other is the prediction of the 0 class. So in reality, you only ever need one of those. You do not need both because they both sum to 1. So the other is 1 minus the other one. So the answer to this one is 1 minus this one. And the answer to this one is 1 minus this one. So they both sum to 1. So in reality, what you'll see if you look at code online, if you look at other people's code, is they'll just grab, I may do this incorrectly. No, that's the first example. They'll just grab the first array of this. Here you go. Now you can see them in a more interpretable way though. So this is one example. This is, and I can't remember which one comes first, but this is the answer. It's predicting 1, so the answer is this one. So this is the probability of 0. The first one is always the probability of 0, and the second one is always the probability of 1. And you can see that in our example, I grabbed the first row, so I grabbed 0. We can do the same thing here. There we go. And the answer is 1. You can see that was the 0th example here. If we look at the second one, and the answer, the probability for 0 should be greater than 0.5. If we look at this one, we can see that is true. It's like 99.9999, very, very confident, repeating. So extremely high probability. So most of the time when people report probabilities, they only report the probability for 1. So they only report the second column. Column here. So they'll slice through, grab everything, but just drop this first column from predict proba because it doesn't add any new information that you can't get from just subtracting from the other one. So it's essentially useless, but it's nice that they give that to you. Some accuracy metrics use that for a little slightly faster computation. So that is predict proba. That is logistic regression. Any questions on this? I had one more comment that popped in my head that I forgot to tell you guys on linear regression earlier today, and I'm looking to see if it's in here, and I think that's why I forgot to mention it. Yes, and I think I do ask you to do this in your homework assignment. Remember, linear regression is our y hat is equal to our beta sub naught plus beta sub 1 times x, plus etc. How do I get these? Beta sub 0, beta sub 1. This is called your intercept or your bias, but in this sklearn package, it's called the intercept. and these are your weights, or in this sklearn package, it's called your coefficients. I keep saying weights and bias because I'm trying to build us towards the neural network terminology, but in linear regression, it's typically called an intercept and a coefficient. This is how you would get those. So our model has a function called model dot intercept. Here's your intercept. And model dot coefficients. I can never remember exactly what it's called. Coef, there we are. Okay, model dot coef, and you're like, whoa, you said y equals 1, and then I got this big long thing, and how many coefficients are there? Well, if you guys remember, let's look at our x. How many features did we have? 1, 2, 3, 4, 5, 6, 7, 8. How many coefficients are there? 1, 2, 3, 4, 5, 6, 7, 8. There's a coefficient for each one. So what this is saying is your median income time. Let me just write the whole formula out here. I think I asked you guys to do this in your homework assignment, to write the formula. Y equals, here's your formula. For this one, it'll be different for your assignments. Negative 37.02 plus, that's our intercept, so that's our beta sub naught. Beta sub 1 is the median income. This is our x times, I'll put the weight in the front because that's how we've been talking about it. Median income, let's see, that's got 0.0, remember there's an e to the 0, 1. 0.04, I'm just going to make them short here. We don't need all this information. There we are, it's round. Plus, let's see, we've got a 0.009. That's not very, we're just going to call that 0. Anything that is less than 0.1, we're going to call 0 for this, just so we can move. Times house age. I'm going to stop after 4, by the way, because I think you get the idea. 0.01 times average rooms plus 0.07 times average bedrooms. Okay, you get the idea. You could finish that formula here with the other 4. The population here, average occupation here, latitude here, longitude here, etc. So if you did this math, if I gave you a median income, let's look at this first one. So how would we calculate what the output was for linear regression? Remember, we're on linear regression. Sorry, I remembered I had to tell you this, so we had to jump over. Negative 37 plus, you could do this on your calculator, 0.04 times, let's see, our median income is 8.3252. And then we would add 0 times 41, which essentially doesn't matter because anything times 0 is 0, plus 0.01 times our average rooms, which was 6.9, I'm rounding here, plus 0.07 times our average bedrooms, which was 1.02, and etc. You would continue to do that for your other 4. It's just a math equation. So then you just add those up, negative 37, and then you add this one, you add the multiplication of this one, which is 0, and somebody could do that and could figure it out. And then we would have an answer, and that would be our prediction. This would be our y hat. This would be our actual output prediction for this first row here. Did that make sense to you guys? Okay. So that's how you get your coefficients, your intercepts, so you can get your actual weights and biases from your sklearn model and say why it makes the decisions that it makes. And I won't say any more, maybe I will. What's interesting about this is you can start to compare some of these, and you can start to say, oh, well, 0.04 is 0 is less than 0.04, and like 0.07 is much larger than 0. Does that mean that 0.07, this feature, which if you remember is our average bedrooms, it has a higher weight, as it has a higher coefficient value? Does that mean that it's more important in our prediction? Does that mean that the model thinks that variable is more important to the outcome? Well, technically, yes, if all of your variables are scaled to be on the same scale. And in this case, they are not. So median income, let's do this. X.describe. Very useful function, by the way. Describe as a function. There we are. Okay. So if we look at this, we can look at what is the minimum value and what's the maximum value for all of our variables. And we can see that there's a lot of variety. So the minimum here is 0.5. The minimum here is 1, 0.8, 3, 0.3, 3. And we can see that the maximum values here range as well. This one gets as big as 35,000, which is very, very different from this other one that only gets as large as 15. What that means is they are not on the same scale. They do not have the same ordinal values. So the number of square footage you see in a house is very, very different than in terms of ordinal value. You could have a house that's 2,000, 10,000 square feet. When you compare that to bedrooms, where you're not going to have a house that's 10,000 bedrooms. Like, you're just not going to see that. And it's not going to occur as frequently, even if you do see it, as a house that's 10,000 square feet. And so they're not on something called the same scale. But so when you have values that multiply by them, we can't say that one is more important than the other. For example, if you add 1 square foot to your house, that's obviously worth less value than adding 1 bedroom. So they're not one-to-one comparisons when we look at the weights that are applied to that, because the weights have to match the scale of those values. So for this one with a really big range, I bet this number is smaller. Let's see. Population. That is our yep, look how small that is. Really, really small, right? A small coefficient, because the range, the scale of those numbers are so big. So you don't have very many dollars that represent one population, or you wouldn't have very many dollars representing 1 square foot in a house. You would have more dollars representing a bedroom in a house, an additional bedroom. And so what a lot of people did is they came up with a way to get around that called scaling, which we'll talk about later in this class when we talk about pipelining and creating model pipelines. And we can put all of these, we can apply math to put all of these features on the same scale. So we can say everything has to range between 0 and 1. It doesn't matter what you are. And what it does is it doesn't change the order of these. So it doesn't move house ages to different orders. Everything occurs in the same order that it was in before. So if one house was older than another, it's still older than another. It just squishes all those values instead of ranging from 3 to 35,000. It squishes those using math down to everything being between 0 and 1. And if we do that, that means everything's on the same scale. And that means I really could say, well, this one has a higher weight than this one, and that means that value is more important. So scaling is common so that people can understand what the weights mean and whether one feature is more important, contributing more to the outcome than another feature. The downside of scaling is, of course, it's not interpretable. So if somebody said, great, what was the population there? In my data set, it's going to look like 0.0079, and we don't know what that means, but you can just unscale it. So you can just transform it back. We just apply the same transformation that we applied to scale it. So it's It's actually fairly easy. And you will see that a lot in machine learning, that pattern, taking some data, applying a transformation to it that makes it uninterpretable for humans so that it's better for the model. And then after the model makes predictions, untransforming it to understand what was the original data if people ask questions about it. But in terms of how the machine learning model processes it, sometimes we transform our data into less human readable representations for better modeling reasons. Okay, I think I had like 3 slides left. Yes, and then I just have some extra, if you guys wanna read a little more about thresholds, I have a couple extra slides at the end. All right. A little context switching because we just talked about linear regression, and then I'm going to go right back to logistic regression. So really challenging that mind switching. I apologize. I forgot to include the coefficients and intercept in that practice notebook. You'll be thanking me on your assignment though. You might ask yourself, great, we trained a logistic regression model. Let me reorient us here. We have this thing called logistic regression, which is a transformation on our linear regression formula, and it bounds our model outputs to a range between 0 and 1 with something called the sigmoid curve. And great, so we get these probability outputs, or we get class outputs, either 0 or 1. How do we know how well our model is doing? You've heard me tell you guys that accuracy is notoriously the worst metric in all of data science. So what are some other things that we can do, or what does accuracy do? It just says, here are our correct predictions over all of the predictions that we made, not taking into account the class imbalance or really any other nuances. Slightly more sophisticated, we could start to look at the true positives, the true negatives, false positives, false negatives. We could start to look at precision, and we could start to look at recall. These are all things that we do talk about in the next class. I want to let you guys know we do come back to this in the metrics session, the 4 weeks on metrics. You guys have heard me say that a lot, so I think you kind of already have an idea of what this class, the metrics session is about. But in very, very short terms, true positives are the instances in which we predicted it was a positive event, and it in fact was that positive event. So in our, we're trying to detect breast cancer, we predicted it was breast cancer, and it in fact was breast cancer. Or we predicted it wasn't breast cancer, and in fact wasn't breast cancer. That's a true negative. Predicted it was breast cancer, it wasn't breast cancer. Now, there are 2 situations in which you can be incorrect, and they're not great in our example of breast cancer. There are false positives. That is where we tell you that you have breast cancer, and you, in fact, do not have breast cancer. That you can imagine how devastating that might be. And it's maybe equally as devastating as a false negative, where we tell you you do not have breast cancer, and you in fact do have breast cancer, and we do not catch it maybe until much, much later, because in the original tests we predicted it wasn't breast cancer. That is a false negative. And what you can do with these metrics is you can combine them in clever ways to make precision and recall. So precision is looks at all of our positive predictions. How many times did you predict breast cancer? And out of those times that you predicted breast cancer, how many of those were true positives, and how many of those were false positives? It's true positives plus false positives over all of our positive predictions. Oh, true positives over true positives plus false positives, sorry. So your true positive predictions over all of your positive predictions. Recall, on the other hand, is the proportion of predictions that you correct, proportion of positive classes that you actually found out of all of them that existed. So if there were if there was a 30% cancer rate, but you only predicted 20% of those, you only found 20% of those, you're missing a third of it. And that would be reflected in your recall metric. So that is how many true positives you predicted out of all of them that exist within the data set. So true positives over true positives plus false negative. I have to look at that. I have the formula written for that one. But recall is looking at, out of everything that exists, how many did you find for your positives? And precision is looking at, of the ones you found, of the ones you did predict, how good were they? Like, how many times were you wrong? So we'll talk about that more. You don't need to know anything about that for this class. Know that they exist. Let them sit with you and we'll talk about it more. Limitations to logistic regression. So still based on our linear relationship, we're just transforming it. We're not doing anything super fancy that would be well suited for nonlinear relationships. So unfortunately, bounding our output between a 0 and 1 doesn't suddenly make our model more well suited for nonlinear relationships. So nonlinear input data. I will say a lot of this is a bit hand wavy because in reality, we just apply this, and if the model performance is poor, then it's poor. And in the domain of like increasingly larger and larger data sets, it kind of works itself out. But I just want you to know it could be not suitable for complex data or nonlinear data. We will look at something called a random forest, which is not a linear model, which will be very interesting to learn about. That'll be another deep dive we'll do into that one. Neural networks are, even though they are essentially a gross oversimplification of a neural network, might be to say that neural networks are a bunch of logistic regression formulas put together. It's not necessarily true, and I think you'll see that, but that could be one way of thinking about it. And because of that, they can do nonlinear transformations because of the complexity. We'll talk about that more, and it could be sensitive to outliers. So in summary, I think the takeaway from here is it's powerful to binary classification. That's the type of problem. So we're classification problems, specifically binary. So logistic regression does not do multi-class classification. It predicts probabilities, and it does that using a decision boundary. And the model inputs are mapped to those probabilities using that sigmoid function, which again is a transformation on our linear regression function. And the cost function to this is log loss, the way those weights are optimized. The one other parting comment I will make is that logistic regression is really, really foundational to understanding neural networks and to understanding how neural networks work. Neural networks are made up of a series of nodes. So you can have many nodes and many layers in a neural network, and each layer is made up of a set of nodes. Say there are 3 nodes in a given layer. One of those nodes looks very, very similar to our logistic regression function. You pass in some features, it takes those features, it applies the sigmoid function to that and produces an output and then continues to pass that downstream. So I promise you the information that we are learning here is very foundational to actually understanding how these large language models and how AI works, which is very exciting. Excellent. I think that is it for today. I am going to stop the recording and then ask if you guys have any questions.